Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on thermodynamics. Previously, we discussed Brownian motion, diffusion, and the kinetic theory of gas. In this lesson, we will be discussing the second law of thermodynamics. If you are ready, we will begin. Time and motion are concepts that we relate frequently in physics. In thermodynamics, we use time to measure the speed of an object's movement or the duration of its travel. But how does time behave? Also, what is the direction of time? Here, two videos are playing that show pendulums swinging. As they swing, you will notice they are moving at exactly the same rate. In fact, the videos are of the same pendulum, except for one difference. One video is playing backwards and the object is moving in reverse. With the pendulum, we don't really notice a difference. It appears as if time has the same behavior moving forwards and backwards. But what about if we throw a tennis ball and record this motion? If we compare the movement of the ball going forward and backward, of course, the physical forces acting on the ball are not the same. It is contrary to our experience to expect to bounce that ball and for it to increase in height as it does when the video plays in reverse. For that to occur, we would need to reverse time's direction. Thus, the second law of thermodynamics was introduced to describe and factor elements such as the forward direction of time. It was also introduced to establish limits on the efficiency of systems and how they behave. To understand the second law of thermodynamics, we must first learn the concept of entropy. Entropy is a measure of the amount of disorder in a system. The measure of disorder is equal to the number of ways this system may be arranged. This is to say, all the potentially random possibilities of motion must be factored in. To account for this, the second law of thermodynamics states no process is possible in which there is an overall decrease in the entropy of the universe. Consider the suggestion of the statement. The implication is that entropy must increase no matter the process. What happens then if we want to reverse a process? When we discussed the concept of ideal gas in the previous lessons, it was made clear that no gas is truly ideal. But there are many that are close enough. While the ideal gas is not a completely accurate representation of a gas we are observing, it is able to provide us with a basic equation that resolves many of our questions about a given substance. Similarly, when using the second law of thermodynamics to discuss processes, we define the processes as reversible or irreversible. A reversible process is one that can be reversed by means of an infinitesimally small change in a property of the system without a transfer of energy. Like the concept of ideal gas, a perfectly reversible process is impossible. Some substances are approximately reversible. However, if a system can respond to a change in its state faster than the change is occurring, it must also have exactly the same entropy. Any change will mean the process can no longer be reversed. All processes that occur in the universe are considered to be irreversible. This means they cause entropy to increase, or there is a finite change in the system. Students, let us do an activity. Can you name some irreversible processes? List as many as you can.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, students. I imagine you have some interesting examples on your list, since there are millions of answers. But can you explain what has changed in each process to make it irreversible? Let us consider some possibilities. Taking a photograph is an example of an irreversible process. Once the aperture of the camera has closed, there is no way to undo the photo we have taken and restore the missing film to the camera. A simple task like pouring one glass of water into another glass of water may seem like a reversible process, but it is not. The location of particles changes. Perhaps some water escapes the glass in the process. Maybe the force of friction generates enough heat energy to evaporate a molecule. Whatever the case, it is next to impossible for the process to remain identical. Therefore, you were correct if you came up with an example in which the process did not repeat. A great number of mechanical devices in the world go through what are called cyclic processes, or cycles. A cycle is an interval of time over which a system is taken through a series of different states before returning to its original state. In this way, engines are able to produce useful work over a large number of repeated cycles. For cyclic processes to be predictable, they must be as close to reversible as possible. Without considering them to be so, analysis of each cycle would be different. It would provide a range of data that is too wide to be useful. Because cyclic processes are not perfectly reversible, no system on a cycle is perfectly efficient. Cyclic processes can also be examined on pressure over volume graphs. The left example demonstrates a gas going through a simple 4-step cycle. The right example shows that in cyclic processes, all work done is equal to the area of the enclosed cycle. We will examine these processes in more detail in our next lesson. Here is one more activity, students. Please match the terms listed to their appropriate definitions.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, everyone. If you are able to match each term correctly, your answers will appear as they are listed here. Here is the definition for entropy. Next is the definition for the term irreversible. The next definition belongs to the term cycle. The following definition is for diffusion. And the last definition is for the term adiabatic. Did you define them all correctly? Good job. This concludes our lesson for today. We have learned about the second law of thermodynamics and introduced some of the associated concepts. Until next time, thank you, teacher. Thank you, students.